Hello, this is Mr. Gilmore with the 8.3, the Pythagorean Inequalities lesson. So in our last lesson, 8.2, we kind of opened an interesting question with our right triangle test, or in other words, the Pythagorean converse. We asked the question, the question that we asked was, could we determine the triangle to be right based on the three sides? But now we want to broaden that question to ask, could we determine what the type of triangle it is based on the three sides? What happens if it's not a right triangle? Are we then able to determine whether the triangle is acute or obtuse? And that's where our lesson is going to lead us today into our Pythagorean inequality theorems. So what if then a squared plus b squared is not equal to c squared? With, again, assuming that c is the greatest value or equally the greatest value, can we then determine the triangle to be obtuse or acute? So let's think about that. And let me kind of give you a rough idea of how we're going to put this concept into then this question into conceptual ideas that lead us into our theorem. So here's the rough idea we can then say. Let's start with the thought of, could we determine it to be an acute triangle? So to make the triangle acute, so we start off with a right triangle, right? Imagine we've got a right triangle then. To make the triangle acute, we need the right angle to then be less than that of a right angle, which means we need to make the right angle acute. Well, the side opposite of our right angle is the hypotenuse. In other words, we're going to take the hypotenuse and shrink it, because when we shrink it and leave the legs the same length, then we'll know that that the angle opposite of that hypotenuse, since it's now shrunk, is now going to be an acute angle when we leave the legs the same length, which means now we have a squared plus b squared is going to be greater than c squared. So that's kind of the rough idea leading us into our first Pythagorean inequality. But moreover, we've got the second thought, which is, well, we go back to that right triangle. Okay, we've got a right triangle. Now we want the angle of the right angle to be an obtuse angle, something greater than that of a right angle, which means we take our hypotenuse and we stretch it. So stretching the hypotenuse, but again leaving the legs the same length, and keeping that c is assumed to be the greater value or equally the greatest value. Now we have c squared is greater than a squared plus b squared, and that's going to lead us into then this idea that we can then find our triangle to be an obtuse triangle. So now we're going to put these two thoughts together and construct them into our two theorems. So let me introduce you to the first of our two inequalities, the Pythagorean Inequality A. Now, inequality, the letter A then in this theorem title stands for acute. This is how we're going to prove that a triangle is then an acute triangle. So now let's let A, B, and C be the side lengths, the three sides of a triangle. And again, we're going to assume that C is the greatest value or the equally greatest value of the three values of the lengths of our triangle. So now if we're given, so here's our conditional at the bottom. If a squared plus b squared is greater than c squared, then we're going to prove that triangle ABC is thus an acute triangle. Now, in reality, we only need to prove that angle C is acute. Okay, we'll be given that since C is assumed to be the largest side, by the converse of ATT, we know then the angles, just by ATT, we'll know that the angles A and B are going to be less than that of C. So if we prove C to be an acute angle, then we will prove that A and B will also be acute angles inherently. So really the goal is to prove that the triangle we have established, that the measure of angle C is an acute angle or less than that of 90 degrees. So here's our setup. Okay, so we're given triangle ABC with A being less than or equal to C and B being less than or equal to C. Again, letting C assumingly be the greatest value or the equally the greatest value of our three sides. And we're given that A squared plus B squared is greater than C squared. So we're going to prove that angle ABC is acute, or really to make this easier on ourselves, we're going to prove that angle C is acute. If we can prove angle C is acute, then inherently by ATT, A and B will be acute. And we will have, so that means we'll have all three angles of our triangle be acute, so leading us then into triangle ABC being an acute triangle. So what's our strategy? It's actually the same strategy we took with setting up our Pythagorean converse, which is let's construct a second triangle. But this triangle, we're going to again construct it to be a right triangle, triangle RST with right angle T, such that we are going to match up our equal pairs of sides. That R is going to be measurably equal to A, and S will be measurably equal to B, thus using our ruler partial to construct that. So now below we've got these two triangles, triangle ABC, triangle RST, such that A is equal to R, B is equal to S. We're going to prove that angle C is an acute angle. In other words, we're going to show that it's less than the measure of angle T. If we show that, then by definition, angle C will be acute, which then lead us to show that angle A and angle B are also acute, and then we conclude that triangle ABC is an acute triangle. So here's our proof. Again, we've got some other things, information given by our construction because of how we duplicated our side measures and how we constructed angle T to be a right angle. Again, we're going to prove angle C is acute. So with the given and the information from the construction such that A is equal to R and B is equal to S, then what we're going to do with our given statement, A squared plus B squared is greater than C squared, we're going to replace A with R and B with S. So now we have R squared plus S squared is greater than C squared. But we know something about R squared and S squared. By the Pythagorean theorem, R squared plus S squared is equal to T squared. So moreover, by substitution, we know that T squared is greater than C squared. Our square root property still works with our inequalities here. So that means by taking the square root and simplifying, we get T is greater than C. That means we have converse hinge to help us out. With converse hinge, we're allowed to compare the angles opposite of those sides T and C. Well, since T is the greater side, that means the angle opposite of angle T is the greater angle. So thus, angle T is greater than the measure of angle C. Moreover, if angle T is a right angle, that means C is then a measure less than that of a right angle. So thus, by definition, angle C is acute, which then can lead us into showing that triangle ABC as a whole is an acute triangle. Because we've assumed C to be the greater or equally greatest value, that means angle A and angle B will have to be less than that or less than or equal of that to C. Thus, we have ourselves an acute triangle ABC, proving our Pythagorean inequality A. Let's move now on to Pythagorean inequality O. The O in this case stands for obtuse. So once again, A, B, and C are the three side lengths of a triangle. We're going to assume that C is the greatest or equally greatest of the three sides, and we'll then show that triangle ABC is then an obtuse triangle because we are going to be given this case that A squared plus B squared is going to be less than that of C squared. The idea, remember, was to stretch the hypotenuse a bit, keeping the legs the same length. So now we move into the setup of our inequality O. So our setup's going to look very similar, only the only difference here is that A squared plus B squared is going to be less than that of C squared, but we're still going to construct in our strategy our second triangle RST such that angle T is a right angle and that R equal to A and B is equal to S. Really, in order to prove triangle ABC is obtuse, we just need to show that one of the angles is an obtuse angle. So again, we're going to show angle C is obtuse. In other words, the way we're going to do this strategically is to show that angle C is greater than that of angle T. And when we do that, since angle T is a right angle, by definition, angle C will be an obtuse angle. Let's take a look at the construction of our proof then. So we have again our diagram, triangle ABC, triangle RST, such that A squared plus B squared is less than C squared. We're going to prove angle C again is obtuse. So with the given and the information from the construction, such that that side A is equal to side R, side B is equal to side S, then take what we're given, A squared plus B squared is less than C squared. Let's replace A with R and B with S. We get R squared plus S squared is now less than C squared. So using the Pythagorean theorem, we know something about R squared and S squared. R squared plus S squared is equal to T squared. So moreover, this time T squared is less than C squared by substitution. And then again with our square root property applying to our inequalities, T will then be less than C. So again, by converse hinge, we'll now be able to say that angle C is greater than that of angle T. And because of that, because the angle is then greater than that of a right angle, we have ourselves an obtuse angle. Angle C is obtuse by definition. So QED, there we have the proof of our Pythagorean inequality O. So to end our lesson, let's just do a couple examples. By given the three side lengths of a triangle, let's test them. Let's see what type of triangle they are. So with the three side lengths of this triangle, 60, 91, and 108, let's classify this triangle as either a right triangle, an acute triangle, or an obtuse triangle. Now, remember, how do we test this? If the sum of the squares of the two sides A and B are greater than C squared, that means we're going to have an acute triangle. If the sum of the squares A squared plus B squared is less than C squared, then we're going to have ourselves an obtuse triangle. And if they're equal, we'll have ourselves a right triangle. Let's plug it in our values. Again, we have to assume C to be the greatest value or equally the greatest value. So we have A and B representing 60 and 91. C is our 108. Let's then plug these in. So we have 60 squared plus 91 squared. We are going to then figure out what is the relationship between some of the squares here in relationship to the 108 squared. All right, so let's then simplify this. We get 3,600 here for 60 squared. We get 8,281 for 91 squared. And for 108 squared, we get 11,664. Adding our 3,600 and our 8,281 together, we get 11,881. We have 11,664. So in this case, our sum of the squares of those two sides are greater than C squared, which then this leads us to say this is an acute triangle. Because the sum of the squares of those sides, a squared plus b squared, is greater, we've got ourselves an acute triangle. Now, let's then move on to our second example. The one mistake students will make is they will assign the c value to the 3, and that is incorrect. C is not the greatest value. We need 4 to be the greatest value, which then leads us to say 2 and 3 can be our a and b values. Now let's plug in our respective values into the position. So we have 2 squared plus 3 squared, and we're going to figure out its relationship to then 4 squared. We have 2 squared is 4, 3 squared is 9, 4 squared is 16. We add our 4 and 9 together to get 13. We have 16, compare them. 13 is less than 16, which then means we've got ourselves an obtuse triangle. Okay, based on what we just proved with Pythagorean Inequality A and Pythagorean Inequality O, when the sum of those two sides is, sum of the squares of the two sides is less than the third side squared, then we've got ourselves an obtuse triangle. And there we have it, just a couple examples using our new inequalities. You'll be seeing more information about these and more examples with using these two theorems on your worksheet. If you do have any questions on the 8.3 worksheet, don't hesitate to email me. With that, be good and do good.